All right. Good. Well, you know what? If this works well, I'm going to start you guys off with a video because I think it's a great way to introduce you to NVIDIA. So let's jump right in.
I am a protector, exploring the expanses of space to keep our planet safe, and all the species that call it home. I am a healer, giving doctors the vision to create amazing new cures. And using the heart's own magnetic field to diagnose itself. I am a guardian, searching a mountain of data to keep us safe when we travel, and a sea of people to find a lost child. I'm a helper, powering autonomous machines that simplify our lives. Capture our greatest adventures. Make us whole again. I am a visionary, enabling taxis that don't need steering wheels, and those that don't need roads. Even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
Awesome. I love that video because it reminds me the fact that, we're an AI, we're an infrastructure company. I build supercomputers for a living. That's what I do. But the reality is when you're in AI, you're in every industry there is. And I'm going to hit you with a lot of examples today because I think that's the best way to really see how far it's come in driving. Now, most of you, if you know NVIDIA or if you have children or nieces or nephews, you kind of know us for this. We're the company that sort of creates gaming worlds. We're the company that has won basically, or been behind the winning of every Emmy for special effects and that you've ever possibly seen. Because we do this. We create imaginations. We help gamers just with a shift of the light have a different experience. We help them think through things. And in doing so, we've been really meeting the needs of probably the most demanding users in the world, and those are gamers. If you've never watched one of Jensen's keynotes and watched the forum where the gamers are on, they're ruthless. Their technology demands are higher than anybody out there, higher than anybody in the data center, I guarantee you, hands down. But what's going on here is we're seeing, how do you create this imagination? How do you do it all? But it's nonstop calculus, nonstop math going on in the background here. The compute demands get higher and higher, because as we create these worlds, whether that gamer looks left or whether that gamer looks right, we have to start creating it out. And stay tuned, we got some pretty cool announcements coming up about this as well. Now, all that is based on this, the amount of compute power that is required. Now, I'm looking around the room, I can see pretty well. If you got as much gray hair as I do, you've pretty much built your career on the blue line. And the blue line is Moore's Law, one of the most incredible technology advancements ever that's happened. And it used to be, I remember coming out with hardware and we say, yeah, the software guys got it so easy because we just keep killing it with the chips, right? We keep killing it with our servers back in the Sun Microsystems days, even back in the Cisco days. Now the challenge is most of those applications were inherently serial, right? So you do one thing at a time, one thing at a time. And through some pretty intelligent processing of that, we were able to parallelize it. But the reality is it wasn't truly parallel. And so that's when, if you kick back to about 2008, when NVIDIA decided to say, you know what, we need a way of taking all this advancement we have in gaming, all this advancement we have in professional visualization, and take that to the world of general compute. And that's when we launched the CUDA architecture. And the CUDA architecture basically enabled you to apply that. So then NVIDIA moved into the world of high-performance computers. And so we started seeing a lot of gains in that way. You started doing molecular design, seismic activities, but it still was really in that other side of the data center, or actually more in a lab. And then in 2012, Alex Krzyzewski of the University of Toronto came out with AlexNet. Competed in an ImageNet contest, won hands down, and really changed all of academia. And by academia, I mean the leading compute places in the world. So the University of Toronto quickly jumped to Stanford. Andrew Ng was at Stanford, decided to go to Google, left Google, went to Baidu, left Baidu, and now is at his own new company, forming new AI components. Fei Fei was at Stanford, she's now at Google. Alex Krzyzewski left the University of Toronto, went to Google, just left Google, went from there, because this world is changing so fast, and these guys are spreading out. Yann LeCun, NYU, runs the FAIR Research Center at Facebook, all massive AI installations. So why that is because if you can take this, what is inherently a serial process, and take what's parallel off that, and take it from the CPU and put it onto the GPU, you're gonna see incredible gains. And not 3x, we're talking 300x. You're seeing an incredible compute gains, and I'm gonna show you some examples of how we got there today. But one of the big things people are faced with, that's great, I see it in AI, and I'm gonna try to give you some examples to show how it's moving out even further. But can you think about your next 5 years? Can you build your solutions based on 10% performance gain? How many people can build out an architecture for the next 5 years and say, I'm going to rely on 10% performance gains? Not many. It's going to be hard to do that. So that's why this approach is coming, and I think it was spot on. This means we're changing your data center. This means we're changing the way you set up your infrastructure. This means I'm going to change your management tools that you guys have gotten used to, because it's all a new ecosystem opening up. And the good news is it's happening pretty fast, and a lot of big vendors are involved, a lot of big customers are involved, and you're seeing really groundswell of open source solutions in here. But it's essential to understand what's going on. All right, definitions. AI's been around forever. AI's been around, if you look at Yann LeCun and his early work, it was basically, artificial intelligence was allowing a machine to do what a human can. Then we moved into the world of machine learning. Most of us are probably familiar with that in the world of spam filters. Spam filters were the ideal machine learning component because we could actually filter out things, we could code what it was gonna be and move it aside. Quants in financial services were the kings of machine learning, right? They could actually come in and manage their trades, see everything was going on, and that got them so far. But then, as I was pointing out, there's only so many Kaggle masters in the world, only so many guys who are really good at doing that. And along came deep learning and changed everything. Now, when we talk deep learning, there's gonna be two sides to it today. There's the training, which you do in the data center, and there's the inferencing, which either can take place in the data center if you're a large service provider, you got a big consumer solution, or it can take very much so at the edge. And one of the best places to see the edge of a data center and the edge of AI is autonomous driving vehicles. So when people think autonomous driving vehicles, everyone goes, yeah, it's detection and action, right? That's kind of what we see and what we think about. But the reality is there's so much going on here. And the best thing, if you could take away from autonomous driving vehicles, it's nonstop predictive analytics. That's truly what's going on. You have to do an incredible amount of models processing, and think of them as microservices. Preparing data, thinking it through, so that when you need to take that action, when you need to do something, that there's there. So let me show you another little video that's gonna kind of walk through all these different components. So the first thing we're doing distance detection. And by distance detection, you got to be able to know, okay, what's my safe space to drive? And that's what I'm now going to go. What's free space? Intersex detection, we're already seeing this. Some of this technology is being rolled out by some of the cars that are in there. Path planning becomes more and more because I want to know where I'm going to be driving compared to everyone else. Lane assignment helps me understand, okay, if I stay in my lane, that's where, again, you're starting to see some of this technology in the cars that are even on the roads today. Dynamic object detection with LiDAR becomes essential, and you can see some of the ways of just knowing where everything is. Mapping and localization is still nascent. Most of the roads that we have driven today don't have enough on it. A lot that's going on about driver monitoring, what we like to call co-pilot, is actually getting stronger and stronger because we can able to read eyes, we can read detection, I can read your lips at 93% accuracy, whereas most humans can do it about 52. This is actually coming out of our component. The personalized HD map is what we were hearing about earlier. If the car knows where you're going, because it's on an HD map, it knows the risks that are ahead. It knows what the conditions are, and then can help you go through that process. Now, if we think about some of the other things that are going on, notice there's a safe driving from an engineer. All the guys who drive our cars are engineers, so we actually have requirements on how they go through the process. But think of this through. You drive your cars, you're capturing the videos, you've probably seen these on the road. There's no way we can possibly drive that many miles. There's no way we can possibly find that many scenarios. Because I could drive that road every day in the summer, and I don't know what it's like in winter when that light is hitting just at a different angle. I don't know what it's like in the rain if I'm the car, because I've learned from my experience. So one of the things that we're actually focusing on a lot now is simulation. You go through the process, you capture what you can in the real world, and then you simulate what you don't have. You apply the conditions that are there. You get that reflection of that sun coming down at that weird angle in the winter where it's just blinding your eyes. That also blinds a car. It changes the way the stop sign looks. So we spend a lot more time now in simulation. In fact, if you look at those 10 models that I showed you, our engineers internally are typically running 10 experiments per model per day. And that's how they think about it. And then what they do is actually figure out what they can no longer get the data for. What I said, there's training and inference. Most people think we start with training. No, we start with inference. We infer across the data. We see which data is great, which data can we label better and use for training, and then we do our training, and we typically go through about 100 experiments, and then we simulate the data that we can't find anymore. That's the world that we live in. Now, this is one of the examples I love is robots. Here in the States, we all grew up thinking robots were going to be evil. You know, the 1950 films, the robot crashing through the living room window after your wife and kids while you're at work on the telephone, all those movies. In Japan, it's the opposite. Robots are heroes, right? If any of us grew up with Ultraman, we know it from there. But if you think about everywhere, they're the caregivers, and they have a cultural reason why, because they have an aging population, and they don't have a generation stepping in to do it. So there's a lot of activity going on how robots fit in. Also in the world of manufacturing, I'm going to walk you through some examples here. One of the first ones we're going to see is Fanuc, where these robots are actually pickers, but they've learned from themselves. And the smartest one, we take the brain and we can apply it to others. For inspection, think about how many oil refineries, bridges, where we actually have people either come down or scaffold up to get to it. This is one that's really cool. Search and rescue. Drones now can detect a human before a human eye can. And if you think about that, if you can find someone in the first 24 hours, their likelihood of survival is great. Warehouse, distribution. Here's a very important one. Millennials aren't eating, so we have to send robots to feed them, right, in San Francisco. But seriously, this is on the streets of Palo Alto and Redwood City in San Francisco. You're seeing these now, delivery. Anybody remember James Gosling, the founder of Java? This is his new company, where they're using this to go out. They send these robots out in the waters, and they can detect things going on nonstop. It never tires, doesn't need to go to a port of call. It just keeps collecting information. This is an intern at NVIDIA. He taught a robot to do yoga poses, pick up cups, which everyone was like, well, why? Well, the reality is those are fine motor skills that they have to learn. And now we have interns being able to teach them how to do that. All that driven off of basically a card about the size of a credit card. And that's the compute power at the edge that's needed for that. Another example in the world of healthcare. By now, you've probably all heard examples in healthcare where your retina is actually the gateway to your health in a lot of ways. It can tell you if you have malaria. It can tell you if you have a potential for hypertension. It can tell you if you have dengue fever just by looking at your retinas. Well, again, so that's great if you have really good labeled data, which we do in the world of your eyes and cancer research, et cetera. It's getting better. But if you think about our heart and the way that we actually monitor that, we tend to use machines that have been out there, and this is an output for your heart. This is your left ventricle pumping blood into your aorta, and this is what doctors look at. It's very 2D, but we're 3D, and that's what you're starting to see here, a 3D indication of data. So if we can simulate the additional activity that's going on, it creates an incredible amount of more of data. And with that data, now we can do deep learning and exploration and analytics on the information of it. And so what's happening now is we're doing a major upgrade. There's about 3 million medical devices in the world, all putting out the 2D components of it. Now, by augmenting these, I'm basically doing a data center upgrade to all the imaging machines that are out there. Now, of course, what we're doing here is we're overlaying the 2D and the 3D information so the doctors can relate to it. There's not, you just supersede the doctors and make this, they can't relate to it anymore. Give them the information that helps them understand the blood flow, what is it when it's dilated, when it's compressed, gives you all that, but they can explain it. They can understand it, which is really, really essential in how they're processing from there. Now, 15 years ago, the compute capabilities of this would have required a huge, huge supercomputer, and this was done just on a few GPUs, actually, this work that we're looking at. All right, more practical example, in the world of sports, chief marketing officers all over the world lay down millions of dollars to advertise in sports, and then they wait about 6 weeks later to find out how that investment went. So they wait 6 weeks, means you're into the next quarter, means there's no way to alter your investment. But what SAP's done with their brand impact is actually they're training on all the logos that are going on. And then as we watch this, you can see it's doing just image detection. It knows how many times from there. Now, a normal human, when you're watching a video, can probably see about 1. Still image, when I still it here, you can probably start catching 4, right? Think about the guys who sit there with clickers and they hit the clicker every time they see your brand. And that's how we've done it for years. And that's why it takes 6 weeks. Now you can actually do it the next day. You can do it in real time if you want it prior to cost that, but real time is, actually slower than next day for batching, right? You can do a lot of these at the same time. All right, so that's all training, and then we get into the video inferencing. This is an example of flower detection. And if you guys are like me, you don't know many of the flowers, but if you actually looked at this and we participated this at a human level, we could probably do it at this rate. You could scan through and maybe do 5 images per second, right? I could look across here and we could shout out names of these flowers and we would probably get to that point. And that meets a lot of solutions, right? So we're looking at here something running on a sky lake and it's doing the inference of it. Now, why you would have to do that? Think about if you're running a CSP or think if you are a consumer product and people are uploading images into your site. You need to make sure, is it appropriate content? You need to make sure is it not copyrighted? You need to make sure, say you are running an auction site and you don't want people to put their phone number on it, right? So you're scanning for our phone numbers embedded inside the picture. That's pretty good, 5 seconds, right? So that means 5 of us could upload things, and we can handle that in a second. Pretty good. Expand that out now. Say I wanted to say just not the people in this room. I wanted to take it out to Montana. I might want to do about 900 per second. Or I might want to do the Western United States. I'm going to need more. Think if you have 1 billion consumers. Think about if you're a Twitter, think if you are a Facebook, think if you are in that space, think if you are a Baidu, think if you are someone that's going in Snapchat. You really need a lot more. Even running on one GPU, 900 images per second, doing the detection is not fast enough. And that's why if you run on 8, we can do about 7,000 per second uploading. What's key here in doing the detection, all that, I don't have the delay. I'm getting to the point where I can process the imaging, do it, and the consumer just sees it as seamless, but it's doing everything knowing what's going on. Now, this isn't just done for flowers. We have people doing this for satellite images, for tracking what's going on in the world of oil production. They have what's going on in the sea, what's going on in roads, just so you know, all in real time. All right, so I want to shift a little bit. A lot of the underlying technology is what NVIDIA does, is we give you the hardware, the software, but then we partner everywhere we go. And one of the most exciting things is we now have 3,200 startups that are completely brand new from the ground up, AI startups, but you're starting to see them be very focused in verticals. And that only makes sense because everything I've shown you so far is very horizontal technology, right? SAP did not invent the technology they used to do brand impact. They saw what was going on in other industries and took it and applied to their products, right? And that's exactly what people are being able to do. Now, you're starting to see this growth of people that are doing practical solutions. In fact, I was just at a VC event a couple weeks ago, and one of the VCs was complaining to me that he's starting to see more lowercase t companies and not uppercase T companies. For him, an uppercase T company was, technology that was specific to a particular company and he could invest in and they would grow. Lowercase was they were more practical applications of the technology. And in my mind, that's a win. That is what we really want to see, more practical uses of it. So if you're looking at AI cities, public safety, image detection, video surveillance, all that kind of components becomes key. But that's the exact same thing that's going on in so many other worlds, right? Silicon Valley, one of the big problems people have is tailgating. Yep. People walking in behind an employee and then stealing something, right? Millions of dollars per year at all companies happens that way. But you already know who your employees are. You already know who their face is. You know when they tag, they're there, but you also can see there's cameras there. So there's processing now. Can you detect, is that person behind them really wearing a badge, not a badge? Things like that just to save a little money. All that's coming pretty quickly. Now, let's shift out of the world of AI and just go back to the big data and analytics space. Right? We talk about processing data, but the reality is most vendors and most solutions, and even the big open source solutions that we bet a lot of things on for years, has kind of failed. And it's failed because it really means I'm going to do things in real time or near real time, which most people, if you go to a conference where they do this, they talk about 10 seconds to a minute. Sometimes if it's really big data, to load your Tableau dashboard can take even longer than that. And sometimes I'm doing queries take an hour, or I go out for lunch and I come back. That's not processing data in a way that you could do anything with. Obviously, it's an unfair comparison when people say AI can do things in the background, the machines, et cetera. But the reality is we need humans to be able to look at data and process it at the speed of thought as well, where you can actually go through the process. Now, what do we do? In the world of technology, we always do it. We have workarounds. When I can't get the technology to do it, we build processes where we segment the data or we do downsampling. And then, how many of you guys have ever heard this? I'm not really sure, but I think statistically, it appears our answer is directionally correct. The data directionally shows that we've done this. So we've paid a data scientist, which are inherently creative people who love to explore data, find new solutions, and we give them tools that allow them to come up with directionally correct solutions, directionally correct components. And so they convince their business guy, this is the best we could do. You start changing the questions you ask to the ones that you can find the data to answer. And really, we're not getting the outliers. We're not getting all those solutions that big data would allow us to truly get to. And that's why we collected all the data. Well, now let me show you an alternative to this. This is a startup. They've been around for about 6 years. A company called MapD. They're one of several database companies that have re-architected and they run on GPUs. They can process the data in a much more parallel fashion. And if you look up in the left-hand corner, this is about a 1.2 billion row database. It's the New York Taxi. And you'll see a lot of people tend to demo on this because it's an incredible data source. I'm going to explain to you up front what happens here because this is how you should interact with data. You should have someone looking at data and someone asking him a question. He goes, well, let's see, and process it. The first thing we're going to do is we're going to zoom in on New York in a particular area. I'm going to get some insights on the drop-offs and pickups there, and you're going to see all the other components. Every time I change one of these, in a normal x86 architecture, it's about a 10-second query per thing you're seeing here, right? So it could take longer. So let's watch. I'll walk you through it. So the first thing, I'm zooming in on the Lower East Side, and it's showing me the amount of drop-off and pickups tends to take place late at night when people are going out on the Lower East Side, right? So I can then do the time sequence down here and see it tends to take place on weekends, right? Because that's when people go out in that area. Now I'm going to zoom back. You can see the number of records go way up. And I'm going to say, well, when do people get dropped off at Starbucks? When I click on that, it then recalculates everything, and I'm seeing that tends to be in the morning. Well, what if I wanted to know when people were dropped off at Citibank? Well, lo and behold, it's mostly during banking hours when they go from there. But not Citibank. Tell me about when they go to ATMs. Oh, again, ATM usage tends to happen late at night in spurts because people have been out in the Lower East Side and then they're going to go out for food and they're going to go from there. That's how we should process data. I should be able to ask, and the guy goes, well, let's look, right? Think about drawing paragons around areas so you can actually just zoom in. That's processing data at the speed of thought. That's when we have nonstop predictive analytics taking place with AI and accelerated machine learning, and then I look at the data to try to rationalize it. I need this sort of compute capabilities to do it. And so we're starting to see some great things in this space. All right. So NVIDIA Compute Platform, what is it exactly? Basically everything from that goes in your PC, started with the consumer cards, our Titan there, to our GPUs, which we then build servers around with all the leading server manufacturers, HP, Dell, Lenovo, Cisco, all have them. We have our own product line, which you see in the middle. The station that we see here is the equivalent of a half a row of servers, if you want to figure from that standpoint. So people do start with a workstation under their desk, but it's really a supercomputer in itself. The final, what you're seeing, is what goes in cars. It's about the size of a CD changer, if you could picture that, sitting in the back of your trunk, and that's what's driving it. And then the other one's the credit card component. So let me show you what we've done to a server, because I think it really changes the view of it all. So this is basically the first 2 petaflop system. 16 GPUs all talking to each other nonstop, because we've put some switches on each of these cards. So I've got 8 GPUs and 8 GPUs all talking across a plane card. Now, what's that mean? If you think about the world that we all built our careers on, it was scale out, right? Where we went through PCIe and, the idea of sharding it across different components. And then the problem there is I have to check back, right? I have to do checksum, make sure everything we're doing okay, and I have to go through the PCIe, and it hits a bottleneck. This is the equivalent of about 1,200 lanes of PCIe communication, all at the same time, nonstop, always. So in effect, these 16 GPUs are acting as one GPU. Now this is why you hear things like feed the beast, because you want to actually be able to pull all that data on there and process it quickly. Now, note there's Xeon processors in here because there's always going to be a parallel and a serial components of it. You have to be able to do both. Now, I show that to everybody, but I'm willing to bet most of you thought, okay, yeah, but to get going in this, I still need to build one of these. I need a row of servers. I need to find room in my data center. The cooling requirements of things like that must be incredible. I got, this is my bottleneck to get started. I'm going to go look for a cloud provider because I can't quite get, this going. Because that's what is still in our heads. And what I got to get people to realize, the equivalent of this, these 300 dual CPU servers, is this. So you literally are making a shift where it's 1/8 the cost, And I tell you, I sit with really, really smart people, and they say, yeah, but the power consumption of a GPU is so much higher than a CPU. Yes, it is, processor to processor. But when you start thinking about the net outcomes that come out of it, it's about 1/18 of the power if I did this comparison right here. So again, when you start getting into massively power processing of data, and that's what we're going to be doing. I think data is the new oil, I hear. Mine is actually data is the new source code. Data is going to be used to really determine what are the feature sets of a lot of software going forward. All right. So with that in process, keep in mind then, it does start scaling out, right? A lot of the Zenuities and the Facebooks who have deployed, they were number 11 on the top green supercomputers in the world a year and a half ago because they put about the equivalent of 300 at that stage DGX1s in their servers. And that got them to be that level of compute. Now what happens? Now you have to start figuring out what all the network components of it are. Now you have to start figuring out what the storage components. That's what brought Pure and NVIDIA together. And you need to start saying, how am I going to start managing some of this stuff? So as I was saying before, one of the great things that's going on is the move to Kubernetes, and everybody understand that Kubernetes is going to be a fantastic solution. Going to be. Right now, Kubernetes is great at orchestration. There's a lot of effort going on in the community to try to get a scheduling capability built out from there. Now, if I was to ask some of my high-performance computing friends, they would say, use Slurm. If I go into a company like Zenuity and say, use Slurm, they're going to go, no way, we're not using Slurm. It's too heavy. We want something more lightweight. We want something completely different. If I go into a company that's been built around Oracle and SAP, and they've got their typical applications in ERP, CRM, they're going to go, we don't use any of that stuff. We don't understand it. So that's the environments that we walk into quite a bit, and that's why you're seeing NVIDIA spending a lot of time working out different data center architectures. That's why we're working with the network capabilities. That's why we're working with the storage capabilities. And then spending a lot of time in the open source community driving here. So we have a pod architecture that I built for the auto because of their demands. It's 9 DGX1s in a single rack, and then the storage inside there as well. So that can be open source storage, can be pure storage, where you're getting a single rack. Well, what does that mean? It changes what a rack is, right? The power density of that rack and the more norm where we will be is about 35K. Most data centers have about 16K racks right now, right? Because we went scale out, we were more focused on that. So there is a change coming even in that technology and how we think through it. But if you're processing that much data, it makes total sense. If you're running a service provider, it makes total sense. And so we're going to see big transitions in there. All right. So a lot of information. I know if any of you, this is brand new to you, and you want to learn more, or you actually have a business leader you want to learn more, or if you actually want to get into the latest of what's going on adversarial networks and how you could do some components, I suggest that you check out NVIDIA's Deep Learning Institute. A lot of this is online, self-paced courses. For large companies, we tend to come in and give training, and it really is just like bringing people up to speed. We understand the transition that's going on. For those of you that are already playing around, for those of you that already have doing it, I encourage you to check out the NVIDIA GPU Cloud. Why? Because many of the things I showed you today are because of the hardware processing, but a lot of it also is because of the software. We take all the leading frameworks, we tune them, we optimize them, and in many cases, it's getting 20 to 30% performance gains over if you had to go out to GitHub and read the 380 pages of documentation on what it takes to download TensorFlow, pull it all together. We've pulled that all together, put it in a container, and it's freely accessible. You can run on any platform that, as a GPU standpoint. So you can run on service providers, you can run on any of the OEMs. We offer enterprise support if you run on one of our equipment, but that's a way to get going and really get started with it.
All right, thank you.